We're going to talk now about calorimetry and how it relates to these enthalpies of reactions that we've been talking about. First, though, let's review a couple of important definitions. Remember, units of energy, typically we use joule, but we can sometimes use a calorie instead of the joule. So 1 calorie is 4.184 joules exactly. And then keep in mind a nutritional calorie. 1 nutritional calorie is equal to 1,000 calories. And notice the difference between those. I use a lowercase c for one and a capital C for the other. Also, keep in mind with these enthalpies, we're dealing with this delta H value. Right? Delta H is going to represent a change in enthalpy for a process. That Q sub P there is heat lost or gained at constant pressure. And we can think about these delta H processes as H final minus H initial. Okay, also for a chemical reaction then, we have delta H of reaction is equal to H of the products minus H of the reactants. Now, when dealing with calorimetry, we have some new terms we have to deal with. We have to look at something called heat capacity, which is going to be represented by a capital C, and that's going to be the quantity of heat absorbed per change in temperature. Okay, so that delta T, remember, anytime we see the delta, it means final minus initial. So delta T, T final minus T initial. All right, so the amount of heat absorbed by some object for a given change in temperature of that object. That's what we're looking at here for heat capacity. You can think in terms of how much heat that material can absorb or store. Right, typical units are going to be joules per Kelvin. Sometimes it'll be joules per degree Celsius. And another thing we have to recognize is something called specific heat capacity. Now that's a lot of times represented by lowercase c. To avoid confusion between that one and heat capacity, I use a capital S. Okay, but you'll sometimes see it that lowercase c. That's going to be that heat capacity divided by mass. Okay, so now we have that quantity of heat absorbed per change in temperature per mass. Okay, and units are going to be joules per gram per Kelvin. And then lastly, we can have molar heat capacity, which is just the heat capacity per moles of material. So the answer to that are joules per mole per Kelvin. The main things we're going to see here, though, are we're going to be dealing with heat capacity and specific heat capacity. So let's consider specific heat capacity. What does that mean? Well, specific heat capacity is going to be different for different substances. Okay, and think in terms of how much energy this substance can absorb per a given mass, per a given change in temperature. So if I look at something like aluminum, aluminum can absorb 0.9 joules if I have 1 gram of aluminum and I change it by 1 Kelvin. Okay, it will absorb that 0.9 joules. Whereas water, if I want to change 1 gram of water by 1 Kelvin, it's going to absorb 4.184 joules. So water takes a lot more energy to heat up than does aluminum. And then when they cool down, that heat will be given up. So aluminum will give up less heat as it cools down than water will, assuming we have the same amount and the same change in temperature. What this means is it's very important for water because water has this high specific heat capacity. That's one of the properties that helps us stay alive. When you think about when you sweat, what's the purpose of sweating? Well, it's to help cool your body off. What happens when you sweat? Well, your sweat is mainly water. So when that water gets on your skin, it's going to evaporate off. Well, in order for that evaporation to occur, the water has to get sufficient amount of energy to go through that process. Now, with water, because it's got such a high specific heat capacity, that means in order to go through that process, it's going to take a lot more energy than, say, gold. So because of that, it takes more energy away from your body, and it helps cool your body that much better. Okay, so that's just a quick discussion of what these specific heats mean and how important the specific heat of water is. Now let's actually get into discussion of calorimetry itself. Well, if you think about the word itself, calorie part, well, that's talking with those units of energies, those calories. The metry part means measurement. So we're going to be dealing with measuring calories or measuring this heat. That's what calorimetry is. We can talk in terms of something called a calorimeter. Well, a calorimeter, if you look at the name, it's some sort of measuring device used to measure calories. So when we look at a typical calorimeter, is kind of a simplified calorimeter. But if I take these 2 styrofoam cups, put them together for insulation, cap it, put a thermometer in them, inside those styrofoam cups, that would be my system, and that's where my chemical process can occur. Technically, outside of that styrofoam cup would be my surroundings. My boundary then would be this styrofoam cup itself. Because the styrofoam cup is providing insulation, I'm going to assume that no energy is going from the system to the surroundings. Everything inside that cup is a system. Any sort of heat exchange that goes on inside that cup is going to stay within that cup. Right? So when we have a chemical reaction that occurs inside that cup, any heat that we see from that, we can readily measure and assume is just due to the chemical reaction. Now, some things we have to get down in terms of calculations for these things. We have to understand how we're going to calculate some of these heats. Remember, heat is represented by Q. So if you have a type of material you're dealing with and you want to calculate heat, and by type of material I mean you have pure copper, pure water, or some specific compound, then you're going to use the equation Q equals ms delta T. Q is the heat, M is the mass, S is the specific heat capacity, and delta T is the change in temperature of that material. If you have an item that's made of multiple components, such as our calorimeter, then you need to use Q equals capital C delta T. Capital C being that heat capacity. So if we have a type of material that we're using and we know its mass, we can use the ms delta T. If we have an item that we're trying to determine how much heat was gained or lost by that item, we use capital C delta T. So let's look at some calculations using these equations. So let's say I have a piece of copper, and I have 1.75 grams of that copper, and I want to heat it from 20 degrees Celsius to 25 degrees Celsius. How much heat would I need to add to that copper in order to get that temperature change? So since copper is a material, I'd use the Q equals ms delta T. Okay, now keep in mind delta T is that T final minus T initial. Okay, so I'd need to know the mass, the specific heat, the change in temperature. Okay, one thing I will probably have to go to my table and look up is the specific heat. But as long as I'm dealing with copper, that specific heat capacity is going to always be this 0.387 joules per gram Kelvin. Now, one thing I want to point out, though, when you're thinking about this delta T equal to T final minus T initial. Or if I look at delta T and I want to know the change in temperature for this problem in degrees Celsius, I get 25 degrees Celsius minus 20 degrees Celsius is equal to 5 degrees Celsius. So what if I wanted to calculate that change in temperature in Kelvin? I can convert my degrees Celsius to the Kelvin by adding the 273.15. My delta T would be 298.15 Kelvin minus 293.15 Kelvin, which would give me a change of 5 Kelvin. And notice, my 5 degrees Celsius and 5 Kelvin, the delta T values are the same. Even though the individual temperature values when I go from degrees Celsius to Kelvin are different, the delta T is the same. So with delta T, we can calculate it for degrees Celsius or for Kelvin, it's going to be the same value. That's only when we're doing it with delta T, and it's only for degrees Celsius and Kelvin. If I had degrees Fahrenheit and degrees Celsius would be different. The delta T's for those would be different. Degrees Fahrenheit and Kelvin, the delta T for those would be different. Okay, so it only works between this degrees Celsius and Kelvin, and it only works when we're looking at this change in temperature. The absolute temperatures are still going to be different. The main point of this is that when we look at these delta T's, sometimes we're given temperatures in degrees Celsius, sometimes we're given in Kelvin. As long as we're looking at a delta T, we're going to end up with the same value no matter which temperatures we use. Okay, as long as we're using that delta T. Alright, so we know we're ending up with a difference of 5 Kelvin here. So we have this Q equals ms delta T. We know what delta T is. We know what S is from the table. We know what mass is from the problem. We plug those in. So 1.75 grams times the 0.387 joules per gram Kelvin times 5 Kelvin. Notice when my units cancel out, what units am I left with? Well, I'm left with joules. Carry out that calculation. I get 3.39 joules. So if I apply 3.39 joules to that copper, I will heat that copper from 20 degrees Celsius to 25 degrees Celsius. Okay, that's what this calculation is showing. Now let's look at a different version of this. Let's say I've done an experiment where I measured a temperature change, measured out how much heat I had to apply to get that temperature change, and I know the mass of an object, and I want to calculate the specific heat capacity of that material. So I can use my Q equals ms delta T. Now I just need to plug things in that I know in that equation. Well, in this case, the only thing I don't know is the S, so plug everything else in. So I've got 5.35 times 10 to the third joules equal to 83.81 grams times S times 85 degrees Celsius. Now I solve for S, and I end up with 0.751 joules per gram degree Celsius. So that would be the specific heat capacity of this material. Now, if it was a pure compound or pure element, I could look up the specific heat capacity value and try to determine which element or compound this material was. All right, let's look at another example. Let's say I want to know the heat capacity of an object that requires 1.26 kilojoules to go from 12 degrees Celsius to 27 degrees Celsius. Well, in this case, since I'm not given a mass, I'm going to use the Q equals C delta T. Plug in what I know, solve for that capital C, and end up with 84 joules per degree Celsius. So that would be the heat capacity for that object. Okay, so those are some basic calculations using that Q equals ms delta T and the Q equals C delta T. Now when we get to heat exchange processes, which could be chemical reactions or other types of heat exchange, another thing we need to recognize is that the total heat lost or gained in a closed system is always equal to zero. So we say Q total is equal to zero. Okay, now another thing you need to recognize is that Q total is going to be equal to all the sources of heat exchange in a system. So anywhere we get heat lost from or absorbed by, those all added together have to equal zero. Right? So let's see an example of this. So let's say we have a sheet of gold weighing 10 grams and it starts at a temperature of 18 degrees Celsius, and we put that next to a sheet of iron weighing 20 grams at a temperature of 55.6 degrees Celsius. And we want to calculate what's the final temperature of those two metals going to be. Now we're going to assume that no heat is lost to the surroundings. Okay, so we need to identify all the sources of heat exchange. So what's going to lose heat, what's going to gain heat? Well, if we look at the gold, it's at 18 degrees Celsius. Are we going to expect that to increase or decrease in temperature when it's put next to that iron? Well, we're probably going to expect that to increase in temperature because the gold is at a lower temperature than the iron. So the gold is going to absorb heat. So we have heat associated with that gold. What about the iron now? Well, the iron is hotter than the gold, so the iron is probably going to lose heat, and it's going to lose it to the gold. Okay, but we have heat associated with that iron. So now let's look at these Qs. How would we calculate Q for each one of these? Well, we're dealing with elements, so we'd use the ms delta T. So we'd have Q of the gold would be equal to mass of the gold times specific heat of the gold times change in temperature of the gold. We'd also have that for the iron. Okay, so we've identified all the sources of heat exchange. We've looked at how we can calculate them. Next thing we need to keep in mind is that all those heats added together are going to equal zero. So Q of the gold plus Q of the iron should equal zero. In other words, any heat gained by the gold is going to come from the iron, and any heat lost by the iron is going to go to the gold. So when we add them together, it should equal zero, right? Because remember, if gold is absorbing heat, that's an endothermic process. If iron is losing heat, that's an exothermic process. Endothermic is going to be positive values, exothermic is going to be a negative value, so when we add those together, it should equal zero. Right? Now, we can also substitute then in those equations we had before. So mass of the gold, specific heat of the gold times change in temperature of gold plus mass of the iron plus specific heat of the iron plus change in temperature of the iron should equal zero. Right? Then it's just a matter of plugging into these equations everything we know and solving for what we're trying to determine. In this case, we're trying to determine the final temperature. Where's the final temperature going to play a part? It's going to come into that delta T calculations. But keep in mind, the final temperature is going to be the same for both of these metals. So we plug everything into those equations, and then we solve for the T final. We end up with a temperature of 50.9 degrees Celsius. Now, does this make sense? Well, yeah, because 50.9 degrees Celsius is lower than the starting temperature of the iron. The iron should have lost heat, which means it should have gone to a lower temperature. That makes sense. What about the gold? Well, the gold should have gained heat, so it should have gone to a higher temperature than the gold, and 50.9 degrees Celsius is higher than the gold. Okay, so it seems like a reasonable temperature. Okay, so that's a basic concept dealing with heat exchange processes. Now we're going to actually get into dealing with chemical reactions that absorb or produce heat.